What do we mean when we say resistors are arranged in parallel with each other? So if we have a circuit that provides separate conducting paths for current rather than one single path, then we have a parallel circuit. So on the left-hand side here, we have two resistors in parallel. And on the right-hand side, we have the same two resistors in a series. Now, when it comes to the electric current within a parallel circuit, the total current from the battery is equal to the sum of the currents through each resistor. But for the series circuit, the total current through both resistors is the same. And we saw this in the last lesson. And I'll put a link in the top right-hand corner if you want to have a look at that. Now, this parallel setup here is common in household electrical circuits because it allows multiple devices to operate independently on the same voltage. If one of our resistors burns out or we detach it from the series circuit, the current will stop flowing. But in the parallel circuit, the current is able to loop back to the negative terminal of the battery so long as there's at least one component or resistor still working in the circuit. In our parallel circuit, the current traveling through each resistor is totally dependent on its resistance, on the resistor's resistance. So imagine resistor 2 has a resistance of, let's say, 1 million ohms or 1 mega ohm, and resistor 1 has a resistance of something really small like 20 ohms. Where do you think the majority of the electric current from the battery will traverse through? Do you think more current will go through resistor 1, or do you think more current will go through the branch with resistor 2? Well, because resistor 1 has a much lower resistance than resistor 2, more charge will flow through resistor 1. In other words, resistor 1 offers less opposition to the flow of charges, to the flow of electric charges than the second resistor. So even though the total current in the circuit is the sum of the current going through each of the resistors here, the current flowing through the second resistor is much, much smaller than the current flowing through the first resistor. So what if we want to find out the total resistance of the parallel circuit? Given that we know the individual resistances of R1 and R2, how could we do this? If we take Ohm's law, delta V equals the current multiplied by the resistance, and rearrange it to make the current the subject, so we have the current is equal to the voltage drop between the terminals of the battery divided by the resistance of the circuit, we can replace all our current terms with delta V divided by the resistance. So now we have delta V for the circuit divided by the resistance of the circuit is equal to the voltage drop across the first resistor divided by the resistance of the first resistor plus the voltage drop across the second resistor divided by the resistance of the second resistor. Now, when resistors are in parallel like this, the voltage drop across each resistor is the same as the voltage drop across the battery. So the voltage drop across the terminal is equal to the voltage drop across the first resistor, which is equal to the voltage drop across the second resistor, and so on. And it doesn't matter how many resistors we have in parallel, they will all have the same voltage drop across them. So with our equation here that we've just constructed, we can divide both sides by delta V to cancel out the delta V term. So whenever we divide a value by itself, we always end up with a value of 1. So this leaves us with 1 divided by the total resistance of the circuit is equal to 1 divided by the resistance of the first resistor plus 1 divided by the resistance of the second resistor. So in order to find the total resistance of our parallel circuit here, where the first resistor is 20 ohms and the second resistor is 1,000,000 ohms, we can plug these values into our formula here and then take the reciprocal of this answer to get the total resistance. In other words, what I've done here is I've rearranged this equation here by multiplying both sides by the total resistance and dividing both sides by the answer that we got, which was 0.050001. So we get a total resistance for this circuit as 19.9996 ohms. Now I've extended the number of decimal places here just to show you that the total resistance in a parallel circuit is always less than the lowest resistance in the circuit, which is 20 ohms in this case. If I'd rounded up this number, the answer would have rounded up to 20 ohms. So let's try a question. A 9-volt battery is connected to 4 resistors in parallel, as shown in the schematic below. Find the total resistance for the circuit and the total current in the circuit. So we've got 4 resistors here in parallel. We've got a 2 ohm resistor, a 4 ohm resistor, a 5 ohm resistor, and a 7 ohm resistor. Our battery has a potential difference of 9 volts. So we learned that the total resistance in parallel circuits can be represented by this reciprocal equation. So if I plug in the values of our resistors here into this equation, 1 over the total resistance is equal to 1.09. And this value has many more numbers after this, which I've stored on a calculator. So when we rearrange our reciprocal equation so that we can make the total resistance the subject, 1 divided by this number gives us a value of 0.915 ohms to 3 significant figures. And again, notice here that the total resistance is smaller than the smallest resistance in the circuit, which is 2 ohms. So now to find the current in the circuit, we can rearrange Ohm's law again. So the total current within the circuit is equal to the potential difference of the battery divided by the resistance, the total resistance of the circuit itself, which we found to be 0.915 ohms. So 9 volts divided by 0.915 ohms gives us a current of 9.8 amps to 2 significant figures. Now, if you watched the last lesson, we had the exact same set of resistors, but they were connected in series. And I've shown this in this diagram here. Now, the current and the total resistance in this series circuit, the total resistance is the sum of the resistors. So we have a different formula to find the total resistance of a series circuit compared to a parallel circuit. So the total resistance for this circuit came to 18 ohms, which is much higher than the 0.15 ohms we got for the parallel circuit with the same resistors. And the circuit's current was again found using Ohm's law. The current is equal to the potential difference across the battery divided by the circuit's resistance, 9 volts divided by 18 ohms. And the current is much smaller at 0.5 amps. In fact, it's about 20 times smaller. And this is because the current can only flow along one path in a series circuit. When you have resistors connected end to end like this, the current is restricted even further. So this shows us that we can drastically affect a circuit's current and total resistance just by changing the arrangement of the resistors or the components in a circuit.